a really unique video today. So I'm going to start off by, I have two cells here that I'm going to execute, and the second one is going to take a little bit to run and execute, so I'm going to execute it now whenever I can. And then I'm going to talk about this and what exactly this is. So this is very straightforward, like AI ABCs. And then how I came about this is there's a lot of research that has come out that has shown recently that AI models are very good at what we would call like inference reasoning, and very good at very bad at deductive reasoning, meaning that they're good at predicting things, of course. They're prediction algorithms, right? But they're not good at understanding semantic relationships between things. And then the reason is that they don't have symbolic reasoning built in, right? There's nothing inherently built into the models that incorporates that or gives them this ability, this symbolic reasoning ability. And when we think about symbolic reasoning in humans, it's very straightforward, right? Like ABCs, shapes, geometry. These are all symbolic reasonings. And then so I started this off very simplistically, thinking about that, right? Like how exactly, what would symbolic reasoning look like for an AI model? Because it would look a little bit different than humans, right? It wouldn't be geometry. AI models, they relate more towards text than shapes or symbols or things like that. So the first thing would be to start there, right? So I kind of I go through this and I iterate back and forth with ChatGPT and Claude and all of this, and then end result I build a full-on transformers model. So this is what we're looking at, right? And this is full-on model. You can see attention mechanism, feed-forward layer. It's got backwards and forwards as far as the feed forwards, and then the backwards propagation, everything within the attention mechanism and transformer layers, right? And then I have embeddings, and then but the specific thing within this is that the embeddings are related to semantic relationships between words, and then all of the attention mechanism and everything else as a result is built off of this concept of semantic similarity. And then so you can see here defining of cat, dog, fish, pet, fur, scales, mammal, and animal. And then I have relationships that I built out, or relations. Is a, has, can, is not, and is to. And then we have context. And then so our context examples are cat is a mammal, dog is a mammal, fish is a mammal, cat is a pet, dog is a pet, fish is a pet, cat has fur, dog has fur, fish has scales, cat can meow, dog can bark, fish can swim, cat is not dog, dog is not cat, fish is not mammal, cat is to fur, fish is to scales, dog is to bark. And then so all of this is related, right? Concepts, relations, and context. And then all three of them are used in essentially training this transformer. So we train the transformer model on concepts, relations, and context, and then the goal is to get it to understand the relations between the concepts and the context. And then so our first iteration was my first attempt at this, right? And then so we run it for 1,000 iterations, and then you can see so this loss rate is, first of all, is very high, and it doesn't really go down. So if we look at this, we would look at this and would say the model's not really learning from this, right? This loss rate is very high, and it's not decreasing at any level, really. And then our cat result is a coin flip. Inference result of cat, a coin flip. Similarity between cat and dog, that's the only one that it gets kind of right. It's saying that there's not a similarity between cat and dog, a really low, 10% chance, which could be a lot lower, right? A 13% chance is still pretty high. And then cat is to fur as fish is to fish, which is pretty good because it could choose any of these concepts. It could choose cat, dog, fish, pet, fur, scales, mammal, or animal. And then so it at least knows to pick fish in this instance, right? So it's doing something within this, and it's if it were random chance, it would probably not just pick fish. And then so that's our first iteration of this. And then our second iteration, I go through and I change a lot of the math in this, right? And then so everything that is changed between this top code and this bottom code is all within the mathematics. I change the initial embeddings, I change the initial initialization, I change a lot of things with regards towards the attention mechanism, the learning rate, optimization, steps, everything across the board, right? Like lots of mathematical changes is what I'm highlighting. Like code, it's not code changes between this top one and the bottom one. It's all math and understanding math, right? And then so everything else is the same. Like I don't change anything with regards to these concepts, relations, concepts, etc. It's all in the math of the training, and then I give it a lot more iterations. So the first one you can see we give it 1,000, and then now I'm giving it 3,000. But even if we were to cut it off at 1,000, as we did before, you'll notice something drastically different with this one, which is that it does start very high, right? It starts at that 7.5, just as the other one did, but almost immediately it drops to 4.3, and then drops to 2.4, and then by the end we get 1.9 as the lowest it goes, but it drops to 2, right? So from 7.5 to 2, which is significant. I would want this to, my next step would be probably to train this for like 5,000 iterations, right? See if we can get this to around like 1, but this means the model is learning, and there's like 100% it's learning, right? Because we can see this loss rate dramatically drop as opposed to that first loss rate, which started at like 7.5, went down to 6. Now we're starting at 7.5, we're going down to like 2.5. Like there's no way that anyone can infer that learning is not occurring here with this loss rate. Similarly, we can see that it creates a negative relationship between cat and dog. It's learning there, right? And then also too, with our last analogy, where it was cat is to fur as fish is to fish, it's now cat is to fur as fish is to fur. So it's not getting it right? Scale would be 100% correct, but fur is moving up on the scale compared to fish. Like fish is above 50% accuracy, we would say, if we were like, that's how we have to measure these things, right? And then fur would be like 80% accuracy, whereas scales would be like 90% accuracy. So like we're getting up there, right? And we're starting to do that. And that's the main point in exercise. Like that's all that this is establishing and showing. There's massive debate around this particular issue, right? Like are AI models, can LLM models, can transformer models, can they learn? Like can they actually learn these semantic relationships? And this is the test that we've set up and that we've established to prove exactly that. That's exactly what we're looking at here. If this transformer model were not actually learning in this instance, we're not actually understanding that there is some sort of semantic relationship between these things, we would not be seeing the results that we're seeing here in this notebook. So it very clearly demonstrates the debate. Is it learning well? No, it could learn a lot better. Like, I'm not saying that these results are amazing on any level, and they're not 100% accurate, but there's 0% probability that anyone can look at this results and look at these two cells in this notebook and say that learning is not occurring, which is exactly what we want with regards towards these semantic relationships, which means that you can teach AI its ABCs, is the bottom line. And if you like this type of content, please like and subscribe. Thank you very much.